Hi sir, good morning.
Good morning. You can call me Suman. You don't need to call me sir. You can call me Suman.
Evening from
Is there a question?
from theory.
You're not really audible. Okay, we'll start in a minute. So I hope I'm audible. Just for hey guys, am I audible?
Yes sir.
Okay. So first 3-5, we'll start. So if you have any questions, then you can either ask me or put it in the chat. So this session will be for 1 hour. We will have it for 12 weeks on Saturdays from 3 p.m. to 4 p.m. So we'll be basically discussing some questions and we'll be trying to solve your like conceptual doubts. Okay, so about me, so I'm a PhD student at the Center for Nanoscience and Engineering at IISc Bangalore. My work is with growth of two-dimensional materials, which are a type of crystals. And you can find me on this LinkedIn ID. I have a web page of myself. And if you have any questions regarding the concepts or the questions discussed here, then you can ask them in the discussion forum and I'll be answering them. So this is the week 1. And we'll be going to just discussing some basic questions about why this course is important and what will you be learning in this course as time goes on over the next 11 weeks. So it's just mostly a general knowledge kind of a question, but you will understand about the importance of different properties of materials. Okay, so this is just some MCQ questions. So this is the first question. What do you think is the answer? You can either type or you can uh, unmute yourself and give an answer. Come on, you can type. I think you have access to type. I'll wait for a minute and then discuss. Okay, somebody says B. So the dash property of the material is still the devices like B and D for certain. C. Okay. So I hope everybody understands what this means. So the iron box is the normal ironing that we do after washing our clothes. The telescope is something that we use to watch stars in the sky. MRI and CT scan is for imaging of our internal body structure. Okay, so I think it's a minute now. So we'll go step by step, option by option. So first of all, what is tomography in computerized tomography? So tomography is defined as producing three-dimensional image of the internal structures of a solid object. So this is something similar to X-rays, right? Within X-rays, we do the same thing. When you have a broken bone or something, we do an X-ray scan to check if there is actually a broken body part. And similar to X-rays, you can see here also that we use waves. Even X-rays are a wave. So we use waves for imaging. And computerized tomography is nothing but doing X-ray from different angles, and then using a computer to stitch them all together. So you can see that. Please unmute yourself. So we'll go step by. Okay. So we know for sure that a telescope is optical, because if you have like lenses and stuff. So this is correct. Iron box is obviously thermal. You use heat to iron your clothes. A magnetic resonance imaging, MRI scan. So this M stands for magnetic. So for sure we use a magnetism, the property of magnetism for MRI imaging. So, and this, however, in the option A, in tomography we see that we use X-rays. We use X-rays for our imaging. And we do not actually need any mechanical part. It's a static part, but you pass X-rays through it from different angles. So we know that this option is wrong. We use here X-rays for for CT scan. So the answer is B, C, and D. I hope so. Different materials have different properties, and so for telescope you need a different kind of a material. For iron box you need a different kind of a material. For MRF you need a different kind of material, and for CT scan you need a different kind of a material, which can emit X-rays. So there's another question. So we have this sensors in our cars and bikes. So which property of the sensors of a ceramic material do these oxygen sensors work on? Any guesses? What is the answer? So we have the sensors. We have something called zirconia sensors in our cars. So we can see that after the engine goes out from the exhaust. So it's located in the exhaust line in the cars. In the bikes also, you can see that they're located along the exhaust lines. This this one, the oxygen sensors. Now, why are they there? And how do they work? Because you can just go to a shop and buy a sensor like this. So but what is happening inside? What is the material property that you actually care about? What is the physics of that material? So come on, guys, make some guesses. And somebody says ionic charge species. Okay, answer A. Anybody else? By the way, if you have any questions, you can stop me anywhere. So I want to take it slow. I want everybody to understand the concepts in all of these questions and hopefully generate some interest. Okay. So first off, why do we have an oxygen sensor in our cars and bikes? So it is to determine the appropriate fuel and air mixture ratio. So it will reduce the emissions, and it will also help us in getting more energy out of the fuel that we put in the bikes and cars. So that is why we have this zirconia sensors in our cars and bikes. So I'll take an example of an undoped zirconia for our for the understanding uh, the species which is responsible for sensing. So what happens? What happens when oxygen comes in contact with zirconia? So what happens is you can write a equation like this. So this is what you have here is oxygen in the lattice, in the crystal of Zr wood. So some part of it is oxygen and go to the ambient, become a gas and leave. Some part of it can create a charged vacancy. So this is a vacancy, a positively charged vacancy in the oxygen site in the lattice. Then you can also generate some electrons. So you can write, like just like any chemistry equation, you can write an equilibrium constant for this. You can see that there is a dependence on the partial pressure of oxygen that this material comes in contact with. You can also do a charge balance so that you know that the net charge that you are left with is balanced. There's no like in the left hand side and the right hand side. So what you get is something like a dependence that goes like this. So what this means is, so this oxygen sensor, this is the zirconia sensor, the outer covering. This is zirconia, and what will happen? Oxygen will pass through it, and it will come in contact with this zirconia sensor, zirconia material, and then because the partial pressure is changing, the concentration of the vacancies, the charged vacancies will change, and then because of this, the current itself will change, and this is why. And by changing the concentration of this charged entities, you change the current, and that is why you need ionic charged species for your sensing material. The current is related with the amount of oxygen that the sensor comes in contact with. Any questions?
Sir,
Yes.
sir, all along we have studied only semiconductors can be doped. Now you have mentioned undoped zirconia. So I didn't understand.
No, what I mean is, so what happens is actually for sensing purposes, people use doped zirconia. People use yttria doped zirconia. It's called YSZ. So it has around 8 to I think 15% of yttria. But and that makes the chemistry a little bit difficult. but it makes the sensor much more sensitive to oxygen. So what I mean is, okay, okay, I mean, I think you're probably confused. So what do I mean by doping of
Yes.
ZrO2, right?
Yes.
Okay, so what happens? Let's say you have some species like calcium oxide, and if you put it in ZrO2, so a calcium can go into the zinc zirconia side. But what happens? It has a positive charge of 2. It is a 4. This is a positive charge of 2, of minus 2, and this is also of minus 2. So what happens? One oxygen site can go to the oxygen site. There's one more vacant oxygen site, a vacancy in an oxygen site. Now what happens? Since we're replacing a plus 4 material with a plus 2 material, it will have a negative charge of minus 2. And because you have a vacant oxygen site there, which would have usually have a charge of minus 2, it will have a charge of plus 2. So you can see here you're again creating oxygen vacancies here, which is, and you are creating here as well. So if you are doping, you make the sensor much more effective in a way. And that is why, generally in what happens is that in the commercial sensors, you will find some kind of a doping in the ZrO2. But this example, just for, because it's the beginning of this course, and probably we have students from different backgrounds, I've considered undoped zirconia for showing that the charge species concentration depends on the pressure of oxygen.
Okay, sir.
Okay. So I do not know if you've come across this term. It's called EMI shielding. So when you have to do EMI shielding of a device, like why, like how do you decide whether some kind of a device is EMI shielding? Why is it important? What do you think is the answer? A, B, or C? It's okay if you are confused, or you can make a guess. What could be the answer of this question? Somebody saying A. A. Anybody else? Okay. So first of all, what are the sources of electromagnetic interferences? What it basically means is electromagnetic waves. And what are the source of the electromagnetic waves? We can see from this diagram that there are different sources which can form this electromagnetic waves, and they can all interact with each other. There are radio towers, there are electric power lines, then there are, you will have microwaves in your house, you will have RF transmitters in different devices in your house. So all of this can interact with each other. And if you have seen a mobile, there's a term called airplane mode. And if you're also traveling in a flight, one of the first thing that they will say is they put your phone in the airplane mode. Why is it called the airplane mode? So it is all related with electromagnetic interferences and shielding. So when you're flying in a flight, your phone's electromagnetic signals can interfere with the controls of the air flight. And because of this interference, there's a chance of having an accident, which is why you need to put your phone in the airplane mode. So it is very important for the flight to have some kind of electromagnetic interferences. So the answer 1 is correct. And so what the shielding looks like is another, you can see that there is another metal layer here. So this is how an internal wiring is shielded against the electromagnetic interferences from the outer from the outer edges. It may be from, say, lightning or microwave, where food is being cooked. It can be telephone towers. And all of this can interact, which is why you need shielding. So the option A is correct here. And you have to, if you want a material for this purpose, you have to design such a material by yourself. You have to find out which property, what happens inside the crystal, which determines whether it's a good shielding material or not, or what property inside the material makes it very prone to being affected by electromagnetic interferences. If there are no questions, I'll go to the next question. Okay. So you would have heard about graphite and diamond. Both of them are carbon materials, carbon-based materials. So, like, which one? Okay, I think it's sorry for this mistake. B, C, D. So do they have similar optical property and similar electronic structure? Do they have dissimilar optical properties and but similar electronic structure? Do they have dissimilar optical property and also dissimilar electronic structure? Or do they have similar optical property but a dissimilar refractive index? What do you think is the answer here? Samagna and Akshat, you both are correct. The answer is C. So even though both graphite and diamond are made of carbon, they are different allotropes. As you can see here, the bonding, maybe I should use a different color. The bonding is different here. However, if you see here, it makes a different kind of a bonding here. Because the crystal structure is different. It's called the crystal structure. Because the crystal structure is different, the properties are very different. Now let us look at some properties of these two materials. See, so the crystal is cubic here, but hexagonal in the case of graphite. It has a sp3 hybridized carbon, whereas it has a sp2 hybridized carbon. And there are some very interesting things, as you can see in the case of thermal conductivity and resistivity. Diamond is a better thermal conductor than graphite, whereas graphite is more electrical conductive than diamond. So if you want to have a thermal conductor, you want to use diamond. If you want to have an electronic conductor, you want to use graphite. In terms of optical properties, we can see that a diamond has a very wide band gap. So what it means is that most of the visible light will absolutely pass through this material. It will not be absorbed by this material, and which is why you get diamond. You see that it has a shiny, transparent. It looks shiny and transparent. Whereas graphite, if you look at it, it's completely black. Like it's probably one of the blackest material, and it's because it has a band gap of 0 away. Whatever light you pass into the material, it is absorbed. And it is absorbed to make some kind of electronic transitions. You should be learning more in this course in detail. So yes, so even though both of them are made of carbon, because of the difference in electronic structure, difference in crystal structures, they have different optical properties and different electronic properties. Do you know any other material which is the same, like elementally it's the same but has different crystal structures, the different allotropes? Okay, you might search it, like whenever you are free, you can just search it on Google. If there are more elements like carbon, yes, phosphorus, right? So we have something called phase diagrams also. If you see that, a material will change its phase from, let's say, BCC to a FCC material, and the properties will also change. So even though from the elemental it's the chemical it's the same, the properties are very different. Okay. So next question. Some materials barely expand on dash because of dash. Stretching because of weak interatomic bonds, heating because low coefficient of thermal expansion, etching because of poor chemical sensitivity, and passage of current because poor electronic conductivity. Somebody has said B. Any more answers, sir? So let's say we have a material. The length of this material is L. Now it can be the stressed, heated, or etching or passage of current. So let's say it increases by the length dl. So this length L can be written as dl can be written as L alpha delta temperature. This is the temperature. This is the length of this rod, and this is the coefficient of thermal expansion. And you can see here that dl is directly proportional to alpha. Okay, maybe I should. And so if the thermal expansion, if Ct is low, the coefficient thermal expansion is low, then even the expansion will be low. So therefore, answer B is definitely correct. What about the other options? Stretching because of weak interatomic bonds. Somebody has said B and D, passage of current, poor electronic conductivity. But you're right, but we're talking about expansion. So if the question was some materials have high resistance, then your answer would have been correct. Some materials have high resistance on passage of current because of poor electronic conductivity. Any doubts in this question?
No, sir.
Okay, can you ask, or you can type it in the chat box? Okay, I think there are no questions here. Okay, we'll move to the next question then. So, what happens inside the material on heating it a little above the room temperature? So I hope it's at 25 degrees centigrade. What happens when you heat a material just above the room temperature? Atoms start vibrating about their mean positions. The amplitude of atomic vibration increases with increasing temperature. Bonds break as soon as any material is heated above room temperature and the material changes its state, or the bond length might increase. What do you think is the answer? Somebody has said A, B, and D. D depends on how you define bond length, I guess. I mean, bond length is a defined concept, right? I mean, it's a length between two different atoms, A and B. Okay, so when you have a crystal, let's say have a square, let's say have a square solid. So it is made up of like structure like this. So it is a mesh of bonds. And if you take any two elements in this, you can model it as a spring. So if you are trying to push them together, then yes, it will apply a force that will try to open up your arms. Whereas if you try to pull them out, then the spring will try to again come back to its original position. So this is the mean position or mean state. When we try to squeeze it, we try to again come to this position, try to expand to again try to come to this position. So this is a spring and a ball case. Similar things also happens for any two particles. So when they're at an infinite distance, this r is the, so let's say you have a particle here and a particle here. It's the difference. So it is the distance between two particles. So if you leave them very far apart, then there will be an attractive force which will bring them together. But after a point, you reach this state. If this is like A, this is like B. If this is B and this is C, you reach the state B here. And if you try to squeeze it anymore, then it will again try to have a repulsive force. It doesn't want to be in that state. And so if you have an energy diagram here, the energy starts increasing, and the particles try to again go far apart. So this mean position has the minimum energy configuration, and the particles will always want to be in this state. Now what happens when you heat the material? So we define what is the mean position, and what will happen now. So when you heat it, you apply some kind of an energy into the system, and when you apply that energy, so you know that anything like atoms try to move, right? So like when you heat it, let's say when you heat ice becomes water. Why does it become water? Because the atoms, the molecules want to move away from each other. And how do they move away? They wriggle. And by wriggling, they wriggle so hard that the mean position increases. The mean distance between them increases. And so option is definitely correct. We know that they vibrate about the mean position. And if you see here now, it is not exactly a symmetric diagram. A symmetric diagram would have looked something like this, but it's not symmetric. So if you, let's say if you move from this position some distance here and some distance here, so in this case the energy will be very high, whereas in this case the system energy will be much lower. So it will prefer to stay in this state than in this state. Or the other way to think of it is, for applying the same energy, if you, let's say you apply some energy that is this much above the mean position, so it will wriggle much smaller distance on the left side compared to the right side. So the particle, so what happens is this part. So what happens is this: if you take this mean position, for applying same energy, this distance this distance is much greater than this distance. And as a result, what will happen is that as you keep applying heat, the mean spacing, this is the, so wherever this dot is there, it shows the mean spacing. So as you keep giving energy to the system, the mean distance between the two particles, if you have two particles like this, the mean distance between them starts increasing and the material expands. So the bond length might increase. This is an answer. So temperature of atomic vibrations increases with increase in temperature. Yes, you are right. Because applying some kind of energy into the system, and that energy is given by Kb into T. It's the Boltzmann constant, and it's the temperature. Generally, it's written in Kelvin. Bonds break as soon as any material is heated above room temperature, and the material changes its state. You know that this is not correct because materials have very high melting points. Some materials, for example, carbon has thousands of degrees of melting point, and it won't. And we are, in summers we have temperatures of as high as 40 degrees centigrade. So, and we are still in the solid state. So we know for sure that the answer B, C is wrong. So the answers are A, B, and D. Any questions? So it's called the Lennard-Jones potential for anybody who doesn't know about it. Now, if you also, now how to calculate these forces? It's written repulsive here and attractive here. So you write, so the expression for this force can be written as F is equal to minus, so in this case it's like d E by, if it's only in one dimension, then dx, where E is the energy. So if you differentiate, you can say that if the force is attractive or repulsive. Any questions?
No, sir.
Okay. So we all have these tools in our home. We have audio speakers, we have fans, and any kind of electric motor. So which property is used for their operation? A and B. A and B. I'll wait for a minute. So when we were in school, you must have learnt about it, right? Motors and generators. We have the Fleming's left hand rule for the motors, and the right hand rule for the generators. So what is a fan? A fan is a motor. When you apply electric field through a wire, you can see here, when you apply electric field through a conductor, and in which the electric field is perpendicular to the flow of current, then there is a force, and this force rotates the coil. And in this case, this force rotates this coil. If you had, let's say, a fan on this side, and then it will also start rotating. So any motor uses both electric currents and magnetic fields for its purpose. So that is for fan, electric motors, any kinds of motor, any kinds of generator as such. What happens is that in hydroelectric power plants, so you have a force, you use the right hand rule in that case. You have the force of water, and in that you have magnetic fields, you have magnets there, and you generate current. So all kinds of motors, generators, fans, any such material uses both electrical and magnetic properties. Coming to audio speakers. So even in the audio speakers, the way that you get sound is that there is a diaphragm, and this diaphragm, it vibrates at a particular frequency, and so this creates compression and compression of air and expansion of air, rarefaction of air, and that pressure differences reach our ears. And if that frequency is in our audible limit, we can hear sounds. And even in this case, the way that you move this diaphragm, and the way that you change the frequency and the corresponding, like higher pitch or the lower pitch, by changing the what is the rate at which this diaphragm moves top and bottom, and that is controlled by the electrical and the magnetic properties. If you would have ever opened up a fan or a speaker, you see that you will find one circular magnet in that, and then we'll find a copper wire wound around it. So the purpose is this for electric current and for magnetic field. Any questions?
No, sir.
Okay. Okay. So what favors the formation of a crystal? Ionization energy due to Coulombic repulsion between ions, due to Coulombic attraction between ions, repulsion rate of inertial cloud overlapping. C, B, C, C. Okay. So we again have the same concept of Lennard-Jones potential when we talk about the formation of a crystal. Now, first of all, let's take an example of what is a crystal. So if we take the case of water, we know that it can stay in the liquid state, it can stay in the liquid state, in the gas state, and in the solid state. Or it's true for any material. It can sublimate to form a gas, it can condense, the gas can condense to form a liquid, and you can freeze the liquid to form a solid. Now, what is the difference? If you see here, in the case of these two, for ease of understanding, the distance between the atoms is very large. Whereas in this case, the atoms are very much closely packed together. So, and it's an ice crystal, right? So the atoms have to come close. So there has to be some form of an attraction. You need an attraction. And now what happens is that, again, if you go back to the same potential energy plot, you can see that the atoms are actually, they themselves will try to pull each other. They will be attracted towards each other. And they will have a minimum free energy configuration. So what happens? Like when you cool down, you will be very close to this minimum free energy position. And if you heat it up at higher temperatures, the separation between the atoms will increase. The main position will be something like this, let's say. And in this case, the interaction between the atoms will be very different and maybe very loose also. And therefore, they can move away from each other and it can be in the gas state. So units and the attraction, the reason for this attraction is Coulombic in nature, because all these atoms are charged species. So the answer is C. But even though Coulombic attraction is responsible for the formation of these crystals, you can see here that there is also a repulsion term. There's also a repulsive repulsion term, because if you take the force here, which is the slope, this F is equal to minus T energy by dx, you see that the force is repulsive in nature. The atoms will try to move away from each other. So the mean distance, the crystals, the lattice parameter or the bond length is determined by both the Coulombic attraction as well as the repulsion. So even though the formation is preferred by the Coulombic attraction, the net lattice parameters, construction of the crystal depends on both the repulsion and the attraction terms. Okay. So I wanted to finish my presentation by in 45 minutes so that we can have more questions from your side. I understand that some of, like it's a since it is the first week, I just wanted to show you that there are so many different properties which are important. So in the first case, you can see that we talk about thermal properties, optical properties, magnetic properties, and then their application. And all these properties, the optical property, for example, if you want a material which is transparent, you will if you want a highly transparent, then you need a high band gap semiconductor. And if you want a opaque material to absorb the light, then you need a very low band gap material or a metal. We know that these metals are a very highly reflective materials. It all depends on the application. So, for example, if we use metals as Faraday cages for shielding against the electric fields. In case of iron box, we need a material which can store a lot of thermal energy. It shouldn't melt at those temperatures also. And there are different applications for magnetic materials. There's different applications for different what kind of waves, what kind of rays you can prepare. Then we spoke that okay, you can even use this engineer these materials for some engineering purposes. In this case, we used it for sensors, or you can also use it for very strategic applications. For example, in space industry. So what happens is that these enemy nations, what they do when we have a satellite for defense satellite, they will try to hack those satellite, or they will try to divert the satellite from its path. And that's some kind of a warfare. And to prevent all those things, they have to ensure that nobody can interfere with the electronics inside. This is the same reason if you look at news about rockets going into space and in the moon, etc. They have a lot of redundancy. They always have 2-3 different computers running the same program, and then they talk to each other to say that okay, the data is correct. This is because when you go to the space, there's a lot of rays in there, their gamma rays and everything, and they can interfere with the electronics. And if it converts a single bit from 0 to 1, then the entire trajectory of the space may be affected, and the mission will be a failure. So it has strategic importance. And then it's not only the chemistry that is important, only the element. You have to also see what is the crystal structure of that. Depending on whether it is graphite and diamond, we show that you can either have a very black material or a highly transparent material. You can have a highly conductive material, a highly thermally conductive material if in diamond. If you have a highly electronically conductive material when you have graphite. And then you can also mechanically bend this material, stretch this materials, heat this materials, etch this materials, depending on purpose. Sometimes good, sometimes it's bad, because if you have, let's say, in safety alarms, in fire alarms, in those cases, use these properties to have an alarm system, so that which depends on the expansion. In that case, you want materials to expand. Whereas if you look at the railway lines, they will have space between them, and if they're completely in contact with each other, then on summers they will apply so much stress that it will be bent, and that bending will cause accidents for trains. So it is bad in the case of railway lines, for example. And then why things expand on heating, and what happens in the crystal? What happens to the atoms when we heat them? So there are further applications. So they can be combined applications as well. You can have to club into two properties like electric and magnetic properties for generating electricity or having motors. And finally, the properties of the crystal, the properties that you want from material, electronic property and magnetic property, depends on the crystal. And how do this crystal form? That can be determined by the simple potential diagram called Lennard-Jones potential. So I hope you have enough motivation to learn more of this course in detail. This is just from the top about what are the applications. With time, we'll be going in much detail into each of these properties. So we'll show why, or what happens when you apply heat to a material in atomic scale. What happens when you apply any kind of like electric potential to it? What happens to that material? Conductors, semiconductors. What happens when you dope a semiconductor? What happens to the resistance of materials, of insulators, semiconductors, metals when you heat them? Do they all have the same behavior? But do they all show different behavior? What does those behavior depend on? We will learn all this. We'll be solving problems on all this in the upcoming lectures. If you have any questions, you can ask me here. We still have around 5 minutes or so. Teams allows meeting of only 1 hour, so I guess we'll have to stop in about 5 minutes. Any questions about anything? I'll be here till the meeting gets over. So if you have any questions. Akshat, Karthik, Shilpa, Tamagna. Okay, so what background are you all from? What is your current degree? What is your expectation from this course? Okay.
Sir, I have done engineering in mechanical.
So you're a mechanical engineer, a bachelor's.
Yes, sir. Yes, sir.
Okay. Your name is Karthik, right?
Yes, sir.
Okay. Nice.
So I too am in engineering, metallurgical.
Okay. So where are you both from? Which place, which institute?
I'm from Bangalore, sir.
Oh, Bangalore. Nice.
Yes.
And you, Tamagna?
I'm from Maharashtra.
Okay. And Akshat, Shilpa?
So I am from Raipur.
Raigad.
Raipur, Chhattisgarh.
It's a
It is
Raipur.
a city. Yes.
Okay. So did you all get a notification for this lecture? Because a lot of people have registered, but very few have come here. So I'm not sure.
We got a mail.
Okay. So if you do not have any more questions, then you can probably leave, or you can stay here if you have any questions.
Thank you, sir.
Okay,
Thank
no
you,
problem. You can call me Suman. So I'm also a student here, so.
Okay, thank you, sir.
Okay. Thank you, Karthik, for staying here. Okay, so nobody's here, so we'll stop the meeting here.